B is us, the optimality-based model, and D is the carbon-based model that I showed, the other one that is satellite-based, but also calculates protection rates from carbon. You can see in terms of correlation, we are actually a bit better than the average. We are almost a bit 0.5, yeah, 0.55, and the average is 0.5, and the other carbon-based models is 0.3. We have a lower root mean square than the other carbon-based, and also even a bit, probably about the same than the average of all models. So basically, we're doing the standard deviation that we have is similar to the standard deviation of the observations. So we're doing as good as the other models for this particular region at least. Then it's a question what happens if you compare for the global map, right? But then for that it will be ideal to have nutrient and light conditions of the global map like the same as the observation, because if you go back to taking climatologies, you're reintroducing all the errors that I wanted to get rid of by having monthly variations.
Can you go back to the figure where you showed that the cells adjust their C2P and N2P ratios? Because I didn't fully understand what the degrees of freedom there are for the cells.
This one?
No, where you actually show that they need to actually go for maximum growth.
You mean the allocation schemes?
Yeah, I think so. Yes. So you say that the cells would try to optimize the phosphorus nitrogen ratio to actually reach maximum growth, if I understood correctly. And that, but that I always thought that is kind of Redfield fixed.
Where?
The C2N, the P2N and the C2N ratio.
In the real cells?
Yeah.
No, that's not true. I mean, no. When you see it in laboratory experiments, they deviate. They basically follow the dissolved components.
Okay.
They only reach Redfield when they have ideal nutrient, phosphorus, and light conditions. And that happens almost never in the real ocean. Therefore, in the ocean, a cell doesn't have any reason to be Redfield, neither physiologically or from their conditions. However, for some reason, they do tend to have an average Redfield. So if you see the average line, the average of the blue points is somewhere around 18, which is close enough to Redfield. Yeah. And the average of the blue line is 15 or maybe even 16, which is close to Redfield. But there's no physiological justification for that. The model is freely calculating the cell quotas. It just happens that the global average is Redfield. But why? I don't know. I don't think there's a reason. I think it's just a consequence of the current distribution of nutrient and light conditions that the cells tend to have Redfield. But beyond that?
Yeah, that no. Okay.
In that figure, you introduced marginal fixation as potential mechanism to generate higher N2P in particular dynamic matter. Why should that be?
They just tend to have a higher nitrogen cell quota. We know this.
And why do they have that in this optimality-based concept?
Yeah. Well, there is an extra allocation or optimization scheme in the model. In the model, I didn't explain it because I didn't use it. But there is an extra optimization scheme in nitrogen where the cells have to decide. So if it will be here, the cell you have an allocation value, and the cell has to decide: is it better for me to uptake dissolved inorganic nitrogen, or is it better for me to uptake gaseous nitrogen, so N2? And so that is what they do. They decide whether. But what we found in those results is that what is reported from those results is that it's either 0 or 1. So there is more like a line like this. There are two optimals. It's either better for them to take the dissolved component, or either better for them to uptake it. And that optimization scheme is an extension of the nitrogen assimilation part. Or
is there some?
Yeah, so it will be an extension of the uptake part.
But why should it lead to more nitrogen in the cell?
Physiologic, I don't know. I mean, I assume that the fact that they can incorporate more nitrogen, they tend to have a natural higher N2C. Why that is? I mean, they can't do it, so it happens to be like that. Maybe they require more enzymes, more proteins, which tends to be, they tend to have a higher enrichment of protein components, which are nitrogen based. I guess that's the best answer.
And by which nutrients are they limited?
Well, but phosphorus.
Yeah. So that it would always also gives some tendency to.
Yeah, that's a good point. If I were to include that, I need to include some kind of phosphorus co-limitation, right? And that will complicate it all. Yeah. So in that case, it's probably better to put it just in a global tripulation model instead of these satellite-based maps, because you have to recalculate the phosphorus variation, which there is no product for that. But it can be done.
When you showed us your diversity map or your adaptation map, there have been other attempts to look at phytoplankton diversity or different kinds of phytoplankton from satellite perspectives and relate those to the geographical provinces. Do you see any relation to these?
Well, I haven't studied those in depth, but the general idea is you have, so from that, basically, from satellites, basically what you can get is cell size. What I heard or what I know from those papers is they tend to tell you that you have small cells in nutrient-limited regions, and because they are small, they have higher affinity because they have a volume biomass relationship, and you tend to have a bigger cells in high latitudes. For the same reason, they don't have such a high nutrient affinity. They have a larger volume to biomass relationship, and therefore the affinity is low. So in that sense, I would expect some correlation between these maps and what these satellite-based products say.
I can have more questions. One is about oxygen. You, in one of your first slides, you said phytoplankton or primary production is photosynthesis is important for oxygen production. Is it important for oxygen in the ocean or in the air?
It's important, yeah, actually for both. I mean, the idea is that oxygen came from phytoplankton in the sea, they produce the oxygen and then it dissolved into the atmosphere. But in this case, I was referring for the ocean and for the oxygen minimum funds. So how phytoplankton can regulate in any way together with physics the expansion or contraction of the oxygen minimum funds.
So what would more phytoplankton do? So more.
Yeah, well, that's counterintuitive actually. The idea is that more phytoplankton and higher production rates will give you higher production rates, which will sort of increase the whole food chain, and because of that, because of the respiration that all this new ecosystem is maintained by the production, then you might actually tend to have lower oxygen. That's just kind of a secondary result of higher production rates. It's not the fault of the poor phytoplankton, they are producing their oxygen.
And then it's pretty often said that the ocean, or we need the ocean because it produces a lot of oxygen. Do you have some idea what, well, land versus ocean? The oxygen?
Because the production rates are about half and half, I would assume that oxygen is related to the fixation of carbon, right? So if the fixation of carbon is half and half, I would assume that the oxygen production is also half and half.
Okay. And then what would happen if suddenly the ocean was dead? You know, you can't production anymore. Would we suffocate or would we feel it?
Will it what?
Would we feel it?
Will we feel in terms of oxygen?
Yes.
Yeah, Eventually. I mean, is that half and half?
Yeah.
But I guess eventually,
What is there right now? What is the net flux, sea flux of oxygen?
I don't really know what it means. I know the calibration time is quite quick. It's about a week. But I don't know the total amount of oxygen flux.
The average of the ocean annual cycle. So what you said already, the fate of organic matter is to die, sink, and be remineralized. And what happens with the oxygen?
Well, the oxygen gets consumed by that.
Yes, yeah. And so basically on the annual cycle, whatever all the phytoplankton that is produced is consumed again. What will that mean to the net oxygen flux?
Also, it will reduce. We wouldn't have that net oxygen flux anymore.
So how can you get net oxygen flux out of the ocean?
By calculating the respiration rates of the organic matter.
Yes, yeah. And which organic matter can only produce a net outgassing of oxygen?
So phytoplankton.
Yeah, but if that decays during the year, it will consume the same amount of oxygen.
So if phytoplankton dies, will it consume the same amount of oxygen that it produced?
Yeah.
That's what you're asking.
Yes. Yeah. So all the organic matter. You just
Yes, I guess so, because they are constraining the whole carbon of the ecosystem.
So if all phytoplankton is respired during the year,
Yeah.
then all the oxygen that was produced is
It's reconsumed
again.
during the same time period.
Yes.
Yeah.
And so that would mean we don't have any chance to have a net benefit from that oxygen,
No.
unless we have to give it back.
Yeah.
But what kind of, there's some organic matter that may help us. So it's not respired
In the ocean.
in the ocean. With the water and sea or sea. So what can we have? Basically organic matter that is not, or dead organic matter that is not respired.
But how can that help us? That is not producing oxygen.
But it doesn't consume the oxygen.
Yeah.
Because it's not respired.
Yeah.
We just block it away from respiration. We just, when we have the benefit of the oxygen that was produced when that organic matter was formed,
Yeah.
but has not consumed, or cannot consume the oxygen again because it doesn't decay.
Yeah. So it probably will be the organic matter in the oxygen minimum funds that cannot be re-respired because of the lack of oxygen.
Yes, that's probably, yeah. And then deeper down.
The benthic environment. I don't know. The anoxic-benthic environment.
Yeah. So the sediment in the mud.
Yeah. That's the benthic. That's not technically the ocean.
Right. How much is that of the total chronic production? Something rough.
Some rough estimate of what is the organic matter that actually is recased.
Yeah.
That's about 1% of the total primary production in the ocean that actually reaches the sediment.
Yes.
I mean, it varies from regions, but I think it's about 1%.
Yeah.
10 or 1. I think it's 1.
Okay. Then it reaches the that's fine.
Yeah.
But finally survives about a tenth.
Yes. It's also it's respired, still on respired in the surface. Yeah. So,
Come back to the primary productivity of the ocean. Do you have any idea whether the primary productivity of the ocean is increasing or decreasing with time?
That's a good. So for the future, so the general idea is that so the general idea is that the picture of the low latitudes will dominate. So the prediction from the models is that it will have higher ocean stratification. And for the low latitudes, that means less nutrients taken into the surface of the ocean, and therefore there should be lower production rates. And the whole idea is that the picture that you see in the low latitudes is expanded toward higher latitudes. However, all those predictions are always made taking or assuming constant red-field stoichiometry. So the idea is what actually will happen if you assume a different type of stoichiometry. Because maybe the growth rate in terms of cell division of phytoplankton might be lower, but if they can be more efficiently taking the carbon by each unit of nitrogen or each unit of phosphorus, then if you just see primary production for carbon uptake, carbon is not necessarily going to be less. If phytoplankton somehow can adapt or acclimate and be more efficient in the way they use their resources to uptake carbon. So the current predictions assume lower primary production rates globally for the future. Again, that's using red-field stoichiometry. If you let variable stoichiometry to happen, I'm not completely sure that will be the picture.
What about the last 20, 30 years? Do you have any indication that the global primary production of the ocean has been changing in the last 20, 30 years?
Well, there was this paper in Science by the people from Canada, and they assume a decrease in primary production, and we will have no more fish by 2050, I think is the prediction. But I think the problem is that they mix different chlorophyll signals, so different ways to measure chlorophyll. So what they say is that the concentration of chlorophyll in the ocean is decreasing, and therefore primary production is decreasing. However, if you put in doubt the chlorophyll signal, then you put in doubt the whole paper. So that paper said it's decreasing. Overall, I think the idea is that it's sort of stable.
How good is this chlorophyll signal from satellite? Can you really measure chlorophyll from satellite?
30% off.
What?
30%. Yeah.
Why?
And it's because it confuses the signal with color organic matter. So sometimes it thinks that's actually phytoplankton is something else that happens to have color, some other type of organic carbon that happens to have color.
That 30% all?
That's
Is there any other reasons why the satellite chlorophyll measurements might be off?
because they only see the surface, and therefore you have the deep chlorophyll maximums and all this stuff, and actually the chlorophyll to carbon ratio that I've been talking so much about, so the chlorophyll doesn't represent the whole signal, so there are many reasons why satellite don't do the perfect job.
So the values that you took is not corrected for any kind of, like taking into account that there's different levels of different depths of the chlorophyll maximum and stuff like that satellites might not see.
It's not corrected by that. You assume that whatever is happening in the surface is the pattern of the mixed layer.
Okay.
What is the role of temperature changes in these figures? Directly on the cell function?
Yeah. So overall temperature, so I'm not assessing the whole community, just phytoplankton, and overall, I believe my growth rates and my respiration terms are both affected by higher temperatures. I don't remember if it's an optimum, but I think growth rate tends to increase with temperature in this model.
Does it have any effects on stoichiometry?
It should have, because temperature is affecting the uptake rates of nitrogen, phosphorus, and carbon. But I believe it's affecting them all in the same way. So then the effect on stoichiometry goes away. So it's affecting growth, but it's not really, shouldn't really be affecting stoichiometry.
Respiration?
Respiration is a cost function of, I believe it's a linear cost function of growth rate. So it just means that the higher growth rates that you have, the higher the maintenance and the energy processing of the cell, and therefore the respiration grows up equitativo.
I was about to ask, is there, are you happy for the questions? You can leave it. Unless you insist. Okay. Then I would like to ask the audience if there is additional questions from your side.
It's fine with me.
It's not up to you to decide. It's not the case. Okay, then I close the exam, and I would like to ask everybody to leave the room.